Okay, well, we're going to start talking about a new topic today called methods. Now, what I want you to think about right now is you've had several weeks of experience writing code, all right? And you're beginning to understand what I mean about the fact that every week you're confronted with a novel set of problems that you have to solve, and there's a real struggle as you're trying to uncrack uh, or crack open the little nugget that's going to help you unravel the problem. And there's a couple things that I want to think about in that process that you're following. One thing is like you might just be wondering every time you take a look at a new problem, you might be thinking, well, how do I solve this problem? The professor's not giving me instructions on how to solve novel problems. The professor is giving me instructions on how to do things in Java. So Java is the tool that you're going to use to solve the problem. But the real hard work is work that you're going to do on your own with this novel set of problems. So is there any kind of process that you can follow? And so far, I haven't really given you a lot of uh, information about a process you can follow because I think that's something that all of you kind of discover on your own. There really is no magical recipe that you can follow to get to the solution to a novel problem. But there are some techniques that you can use that can help you get closer to solving a problem. One thing I'd say is understand the problem. If you don't understand the problem you're being asked to solve, then it doesn't make a lot of sense to sit down and start writing code, right? Because the computer's only going to do what you want it to do. The computer can't make intuitive leaps like you can make. And the computer doesn't understand anything special above and beyond what you tell it. So if you don't deeply and thoroughly understand what the problem is asking you to do, it's going to be really hard to solve the problem. Another thing that you can do is use paper and pencil first. All right. So what I mean by that is as you're going through the process to understand the problem, particularly, for example, like a math problem, all right, the question is like, if you think you're really understanding the problem, can you with paper and pencil solve the problem on your own? I mean, don't worry, you don't have to worry about all the steps you're taking to solve the problem, but like given an input, an sample input for the program, can you work out the solution with pencil and paper? Like, because that's going to really show that you understand the problem. The third thing that you can do is start out small. Okay, so what I mean by that is instead of trying to solve the whole problem all at once, and you're thinking about all the different things that you need to do in order to get the answer, that is really overwhelming. And computer scientists don't approach problem solving that way. What we've figured out is that like we can only work on a little bit of a problem at a time, and if you get that little bit of the problem working, then that's going to move you just a little bit closer to solving the problem. And so if you start out small, what you want to do is then run your bits of the program frequently. So I'll give you an example. So I was working with a student. From the other section who was working on the coin flip problem, which is a problem that's due for all of you. It's due this week, all right? And so for the coin flip problem, there's a couple of different things, right? First of all, like, do you understand what the coin flip problem is asking you to do? And what it's asking you to do is flip a virtual coin a bunch of times and count up the largest run of heads across the run of the coin. So if you flip the coin 10 times, you want to count up what is the largest number of times that the head appeared continuously, okay? So here's what I mean by that. If you have 0, 1, 0, 0, 1, 0, 1, 0, 0, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so if that's an example run of your coin flip program, where a 0 means heads and a 1 means tails, and the description of this is in the problem description. But basically, you're flipping a coin and generating a random number. A 0 means head, a 1 means tails. So there's a lot of stuff going on here, but the goal of the program is to count the largest continuous streak of heads, all right? So if 0 is heads, this is the largest one, right? That 3. Now, how you do that, starting out, it's pretty overwhelming to think about how to solve that problem, right? But the first thing is, do you understand the problem? Well, I hope just with the description I just gave you that you do understand the problem, all right? So we're flipping a coin, a 0 with a random number generator that basically returns a 0 or 1. So a 0 means a head, a 1 means a tail. If you flip the coin a bunch of times, you can get runs of heads and tails, and we want to know what the largest run of heads is. So I wrote down 10 flips here, and I just indicated, well, those 3 heads at the end, that's the largest run. Now, how do you tell a computer to do that? Well, that takes some work. But if we start out small, maybe we can, just slowly but surely move along towards solving the problem. So if you focus on trying to get the whole problem solved at once, you're not gonna solve the problem in a timely manner because you're gonna be thinking about all the different things that you have to do. But let's talk about some simple things that we could do to try to get this coin flip problem to work. So like number 1, can you flip a coin? Right? That's a good first step, right? Number 2, can you print out a run of flips? Okay, that's pretty useful. Number 3, can you count a run of heads? Okay, so each one of these steps, I'm not saying that this is not the solution, but each one of these steps is getting you a little bit closer to solving the problem, all right? It's a really big leap to go from a blank screen to I'm counting the number of the largest run of heads in a coin flip program, all right? That's a big leap. So do little bits, like think about it, right? If you've never written a program to flip a coin, just getting and count up the number of heads, just getting the program to flip a coin, that's a big deal. So just write a little bit of code, see if you can get the program to flip a coin. That's going to feel really good. Then, all right, if you flip the coin once, can you get the program to flip the coin a bunch of times? If the user tells you how many times they want to flip, can you flip the coin that many times? If you can do that, that's huge, right? So you've moved a little bit closer to the goal. And then number 3, counting the number of runs of heads. Well, that's a little more complicated, but if you instead of trying to do that right away, if you build up to that, you're going to become more and more familiar with the problem and techniques to solve the problem, and it's going to move you in the right direction. Now, this isn't a perfect recipe for solving every problem, but it is a very useful technique. Now, you might be wondering why I'm bringing this up. Well, the reason why I'm bringing it up is because I want to talk to you about techniques for solving, one of the techniques for solving problems, which is this idea of taking a problem and kind of breaking it out into smaller pieces. And what you're going to find now is you're getting to the point as a programmer where the amount of code that you're capable of writing to solve a problem could be very large. And in fact, in the homework assignment that's associated with the methods lectures that we're doing this week, which will be next week, that homework assignment is going to ask you to write some programs that you are going to, they're basically like the biggest programs that you've written to date. There's a lot of code that you're going to write. And once you start writing lots of code, it gets hard, really hard, to manage all of that code. It's really hard. And so there's a few techniques that programmers have developed to help with code management. And one of them is this technique called methods. And so what methods do is they take code that someone else has written or code that you've written, and they gather all that code up and they give it a name, kind of like a function. Like if you were to think about like my mother-in-law is calling right now. I'm gonna let that go. Okay, so she's awesome, by the way. All right, so anyway, so for example, if I were to write if I were to write a for loop to sum up the numbers from 1 to 10, that would be that would occupy some code, right? But I could also give that for loop that sums up the numbers 1 to 10. Maybe I could give it a name called summation, or better yet, let's do this, sum. And if I write the word sum in my program, it will automatically sum up the numbers 1 to 10 and print them out on the screen. So this word, sum, is a stand-in for the code that adds up the numbers 1 through 10. All right? Now, that shouldn't seem that weird of a concept because in high school math, you worked with functions, right? A sine function, a cosine function, tangent function, square root function. All of those functions had words associated with them, right? Square root, or a symbol, square root, or sine, S-I-N. And those words were stand-ins for a set of mathematical operations to do something. So that's what methods are. Methods are simply just a name that represents a chunk of code that does something. Sometimes that name is associated with code that you write, and sometimes the name is associated with code that someone else wrote that you're using. So to start out, we're going to look at some code that we're going to look at methods that you can use in your code that someone else has written. But as we move along, I'm going to introduce a technique that you can use to take code that you've written and place that code in a method. And what I find when students start being asked to put their own code in methods is there's a little bit of a resistance, because you can write a main program and all of your code can be in the main program, which is wonderful. But once you write a lot of code, it really gets hard to manage it all. So taking some of your code out and putting it in a method, giving chunks of your code names that you can then call in your main program, it's going to make your code a lot easier to read and understand. All right, well, so let's get going. I kind of introduced the idea of methods, and I said that methods are going to help you with problem solving by taking code and reducing it to a name, and that makes it more easy to manage. All right, and you're going to need this because pretty soon you're going to be writing really big programs, and it's going to be hard to manage all that code. So let's look at an example of using someone else's method to solve a problem and how convenient it is. Okay, so here is a picture. I guess I'll draw a picture here of, here's the Earth. All right, and here's a sailboat. I like sailboats. Okay, and the sailboat's sailing along the ocean. And over here, I'm going to just draw a line here. Over here somewhere, there is a there's a cell tower. Now, I don't know if you know this or not, but if you get on a sailboat and you start sailing, as long as you're near the coast, you're going to get fairly good cell reception. So I have friends that take pictures of stuff that they're doing on their sailboat and they post it on Facebook or Instagram or whatever, and that's really cool. And we do that too. But at a certain point, if you sail far enough away from land, you will not be able to get access to the cell tower anymore. And the reason why is that the Earth is round. So as you move away from the cell tower, at a certain point, your cell phone antenna will not have a direct line of sight to the cell tower because of the curvature of the Earth. So when the sailboat's over here, we don't have access to this cell tower that's over here. All right? And if you're far enough away from land, you don't have access to any cell tower. So you lose your cell reception. All right. And so the question that I'm kind of curious about is, if you're in a sailboat and you're starting to sail away from land, how far away do you have to go before you will not be able to get good cell reception anymore? That's the question. All right. And so to answer that question, we are going to put together, just kind of draw a little diagram here. So here's the center of the Earth, and here is the distance from the center of the Earth to the sailboat, and that is the radius r. And here is another r, and this is a right angle, by the way. Here's another r, which is the distance from the center of the Earth to the base of the cell tower. And the cell tower itself has a height h. And then we have a distance here, d. All right, this point right here is the maximum distance we could be away from the cell tower before we lose cell reception. If we sail any further in this direction, we're going to be out of sight of that cell tower. All right, so we can just write an equation here using Pythagoras' theorem. R plus h squared equals r squared plus d squared. Now, I would say at this point, the hard part about solving this problem, like writing a computer program to solve this problem, we've already done it. We've done the hard work. So the hard work was making an observation about what is the longest distance that you can be away from a cell tower before you lose reception. And that's basically the point at which this tangent to the sailboat intersects the cell tower. All right, the tangent to the circle, that is the Earth, intersects the cell tower. And then recognizing that we have these r values, which is basically the radius of the Earth. That's the hard work to solve this problem. The rest of it's just a little bit of math manipulation. So if we square these things out, first of all, what are we solving for? We're solving for d. We want to know what this distance is. So if we solve for d, we're going to end up with, d equals the square root of 2rh plus h squared. Now, I'm going to make some simplifying assumptions just to make things, the math a little bit easier. R is a really big number. I mean, we're talking about thousands of miles. And h is a really small number. H is like in feet. And so h squared is really not a meaningful contribution to this distance calculation, because it's just going to be some number of square feet, but r is so big that it's going to completely dominate this expression. So we're going to simplify this to the square root of 2rh. All right, and then with a little bit, we can plug in 2 and we can plug in r, and then work this out. And so we're going to end up with 1.23 times the square root of h. That's what the distance is, all right? At which point we're going to lose our cell phone reception. All right, that's the distance in miles. Okay. All right, so cool. That's super great, super helpful, but now we have to turn this into a computer program. So what is the computer program going to do? Well, the computer program is going to say, hey, what is the height of your cell tower? And then based on the height of the cell tower, we're going to compute how many miles away you have to be, or how many miles away that D value is, okay? I hope that makes sense. And remember, the hard part about this, the amount of code we have to write to make this work is fairly trivial. The hard part about this program was doing all the derivation work to discover what is it that we want? We want D. Okay, how do we get D? Well, we need the radius of the Earth, the height of the cell tower, all that stuff. That's the hard problem-solving part of this problem. Okay, so let's bring up Codio.